Okay, so this is episode 1.3. We're going to be looking at systems of linear equations and their representations using linear transformations and matrices. So back in the first episode, you remember we covered how matrix multiplication works, and so you can see down here that when we take this matrix here, A, B, C, D, and multiply it by this vector x, y, then what we're actually just taking is a linear combination of the columns. So of our column vectors here of A, B, and C, D. So here our result is x times our first column, A, B, and y times our second column, C, D. And so that actually leaves us with a nice way to represent these systems of equations, because we can consider this here, so this pair of equations, 3x plus y equals 6 and 2x minus y equals negative 1, by writing x times the vector 3, 2, because you can see that that's our coefficients here from this first row here, and y times the vector 1, negative 1, because that's this column here. And you can see that we have 3x, so 3x plus 1y is 6, and here we have 3x here plus 1y, so we have 6 here. And of course on the bottom, the same way, we have 2x minus y is negative 1. So our equations become this. Or if we want to reduce it into matrix form, we have that 3, 1, 2, negative 1 multiplied by the point xy is equal to the point 6, negative 1. So asking the question to find the solution to this system of linear equations is actually the same as asking what point, when undergoing this linear transformation, or when being multiplied by this matrix, is equal to the vector 6, negative 1. Okay, and so now we know that, we can look at some other ways of solving these equations using matrix methods and using linear transformations. Okay, so let's take a look at exactly what it means to solve an equation like this. So here we have that V is some linear transformation whose matrix is written here on the right, and we've got this set of linear equations here where we have V times xy is 5, negative 2. Okay, so let's just expand V times xy. So V times xy is going to be x times our first column vector here, which is going to be 2, 1, plus y times our second column vector here, which is going to be 1, negative 1. And that's all going to be equal to 5, negative 2. Cool. So what that actually means here is if we draw in the vector 2, 1, so here I'm going to draw 2, 1 in blue, so I'll just write it here in blue so we can remember. 2, 1. Okay, so 2, 1 looks like this, and 1, negative 1 looks like this. And so here what we're asking is, what x and y do we need to have x lots of 2, 1 plus y lots of 1 minus 1 is 5, negative 2. So we could imagine adding together multiple copies of this vector here and multiple copies of this vector here to try and get down to this point 5, negative 2. And so let's just take a guess at that. Well, if we were to use one of these blue vectors, we'd have this here, and then we might take another few of these red vectors. Okay, cool. So now we have that 3 times 2, 1. Sorry, we have that 3 times 1, negative 1, which is this red vector here, plus 1 times 2, 1 is equal to our vector 5, negative 2 here. And that would be the same which direction we came from, because even if we added this one here first, this vector here first, we'd just be coming down here 3 times. So it'll put us in the same spot. Okay, so that is actually what we're doing, is we're trying to find some combination of these two column vectors here, that when we add, a times the first one or x times the first one and y times the second one, we're going to get to this vector here. So that's actually what our problem looks like. Okay, so these here are some important linear transformations. So they're important. The reason that these are important is actually because they are linear transformations and what they represent. So if we look at this first linear transformation here, we can see that all it's doing is scaling the x component. Right, so all this transformation does is stretch out the x component of the vector that goes in. Similarly, this transformation down here stretches out the y component, so it just multiplies the y component by some constant. Over here on the right side, we have that t here is a linear transformation where all we're doing is taking our top row here, or our top number here, and we're adding some multiple of whatever the bottom number is to it. We can see that that's a linear transformation. Similarly, the bottom here, we're doing the opposite, so we're just taking the bottom and we're adding some multiple of the top to the bottom. Now, these here it's important that these are linear transformations, because when we take something like this, as in this system of equations here, and we convert it to its corresponding vector representation, so here we have 3, 2 plus y 1, negative 1, we have that that is equal to 6, negative 1. That when we apply any one of these transformations to this equation as a whole, so we apply the same transformation to both sides, we can see that the transformation itself can actually just distribute, and we can just modify these vectors here under that transformation. So let's use this transformation here, and so we can see that we can take any amount of the bottom row we want, so this y, and we can add it to the top one. So here we would imagine that a is 1, so we would take the transformation t xy that takes the point xy to x plus y, because a would be 1, y. And so if we apply that to all of these vectors, we get that x times 5, 2, because remember we're taking the bottom number and adding it to the top, plus y times 0, negative 1, equals 5. So, equals 5, negative 1. Okay, so that gives us this here. Now, we can continue that over here by seeing that, yeah, okay, we can also scale the top row, just like we have in this first linear transformation here up in the upper left-hand corner. We can scale the top row, and that's a linear operation, so we can apply it to this side here. So we can apply it entirely to both sides, and it'll distribute. So that means that we have x times 1, 2 plus y times 0, negative 1 is going to be equal to 1, negative 1. Okay, let's go to the next step. We can take this transformation here. So we can take one lot of this top row, effectively, and, two lots of this top row and take it away from the bottom. So we would end up with x times 1, and then here we'd end up with a 0, because we're looking at this one here. And so we've got our a as negative 2, plus y times, and then apply our transformation again, 0, negative 1, because we'd be taking away 2 times 0, equals 1 minus 3. One more, if we scale everything on the bottom by minus 1, by using this transformation over here, we end up with x times 1, 0 plus y times 0, 1 equals 1, 3. And this equation here is particularly important now that we've reduced both of these column vectors to 1, 0 and 0, 1, because it tells us that x times 1, 0 plus y times 0, 1, that's all just xy. So if I erase all of this stuff, we now just have that xy is equal to 1, 3. And that tells us that we have the solution x equal to 1 and y is equal to 3. Now, we're actually going to take this method here and we're going to convert it. We're going to put everything in a matrix, and then we're just going to do like basic operations on it. So we're going to like abstract this problem a little in the next episode to make it easier to handle. Okay, so let's just think about what these transformations, before we go to the next episode, what these transformations, what their corresponding matrices would be. So this one here, it takes xy to axy. So that means that we get axy, well, that's just this, isn't it? That's just x times a0, because we've got ax and the 0 on the bottom, plus y times 0, 1. So here we can see the left-hand side of our matrix is going to be a0, and the right-hand side of our matrix is going to be 0, 1. And so that's what this transformation here is associated with this matrix. Similarly, this matrix down here is going to be it's going to be 1, 0, 0, a, just like that. Because here we've got we've got x lots of 1, 0, or 1, 0 lots of x if you want, and a lots of 0, 1. So a lots of this vector here. Okay, this transformation here, you can see that that's actually just, use red here, that's actually just equal to x times 1, 0 plus y times a1. And so that's going to be equivalent to the matrix 1, 0, a1, like that. And similarly that this matrix here, that this transformation here is going to be equal to x times 1a plus y times 0, 1. And so that's going to be equivalent to the matrix 1a, 0, 1 rather.